Every application running right now generates a continuous log of its activity. But when a service fails, those critical records are typically packaged in massive, compressed archive files that are difficult to access quickly. The standard approach involves extracting these gigabytes of data to a local drive and waiting for the decompression to finish, only to find that the resulting text file is too large for most editors to open without crashing. We can solve this by writing a Python script that reads the compressed data directly in memory. This allows us to synthesize a full report on the fly without ever writing an uncompressed file to the disk. To follow this process, you will need Python 3 and a standard code editor. You can use the sample.gz file provided in the video description to test the logic. Mastering this script gives you a way to transform a dense, unreadable data archive into an immediate diagnostic summary. Open your editor and define the file path variable. This points the script to the specific location of your compressed log archive. Now, import the gzip and JSON libraries. Gzip provides the interface for reading compressed streams, and JSON will allow us to parse the structured text found within each log entry. Now, we need to initialize our trackers. Create an empty list called latencies to store response times, and an empty dictionary called status counts to record HTTP response code frequency. We use the gzip.open function within a WIF statement. This ensures system resources are managed efficiently, opening the stream to read data and closing it once the script finishes. The configuration of this stream is precise. We use the RT flag for read text and specify UTF-8 encoding. Without these, the script would only see raw binary. With them, the compressed stream is decoded into readable characters in real time. By defining this specific connection, we have created a direct pipe to the system data that avoids the overhead of the local file system. Next, we establish a loop to iterate through the file one line at a time. This keeps our memory usage low, as the script never needs to hold more than a single log entry at once. Log entries often contain trailing whitespace or newline characters. We use the strip method to remove these from the edges of our data before processing. We also need to account for blank lines, which can cause errors during parsing. Adding if not line continue tells the script to skip over any empty entries and move to the next valid line. We convert each line of text into a queryable dictionary using json.loads. This step translates the raw string into a format where we can target specific data points by their keys. We target the latency key and add it to our list. Using a default value of 0 ensures that the script continues running even if an entry is missing this specific piece of information. We apply the same logic to the status key. By using the dictionary get method, we update our tally of server responses, incrementing the count for each unique code the script encounters. This looping process is the core engine, filtering thousands of lines of raw noise into a cleanly structured set of metrics. Once the loop finishes, we need to calculate the average latency from the numbers we've collected. If the log file was empty or contained no latency data, a standard division would result in a zero division error, causing the script to crash. We handle this using an inline conditional. If latencies, else 0. If data exists, the script performs the math. If not, it branches right and simply returns 0, keeping the execution stable. To build the final report, we use print statements to display the total number of requests and the count of entries that included latency data. We use the :.3f syntax when printing the average. This ensures the output is constrained to 3 decimal places, which makes the final report much easier to read. Finally, we iterate through the status counts items. By wrapping this in the sorted function, we ensure the HTTP status codes are displayed in sequential order. Raw numbers are only useful if they are organized. This formatting is what converts mathematical totals into a report that an engineer can use. Save your work, open your terminal, and run the script. The script executes instantly. You see the total request count, the precise average latency, and a sorted breakdown of status codes recorded in the archive. This output provides a high-level view of the system's health. You can see if latency is spiking or if 500-level errors are frequent, pointing you toward the specific areas that require a deeper look into error traces or request payloads. Because this logic is memory efficient, you can easily wrap this script in a loop to process an entire directory of logs, allowing you to analyze hundreds of files at the same time. You now have an automated tool capable of parsing massive data sets in seconds. Use it to streamline your next diagnostic session.